Hello, and welcome to Summarize Science, where we break down fascinating research. Today, we're diving into a paper that explores how our uncertain knowledge of the first stars challenges our ability to hunt for primordial black holes. Scientists are getting ready to observe something called the 21-centimeter signal. Think of it as a cosmic fossil, a faint radio wave left over from when the universe was in its dark ages and the very first stars were just beginning to form. This signal is extremely sensitive to the temperature and ionization of the gas in the early universe. Because of this sensitivity, it could be a perfect tool for finding exotic physics, like primordial black holes. These are hypothetical black holes that may have formed right after the Big Bang. If they exist, they would have accreted matter, releasing energy and heating the surrounding gas, leaving a distinct fingerprint on the 21 centimeters signal. However, the paper highlights a massive challenge: the astrophysical uncertainties. The truth is, we know very little about the universe's first stars. Were they bright or faint? Did they produce a lot of X-rays? These unknowns create a sort of background noise that can be confused with a signal from new physics. To demonstrate how significant this problem is, the researchers created 3 different plausible scenarios for what these first stars were like. One scenario, which they call more constraining, assumes the first stars created a very strong, clean 21 centimeters signal that is easy to detect. Another, the less constraining scenario, assumes the stars created a weak, shallow signal that is very hard to distinguish from instrument noise. Here you can see the huge difference these assumptions make. The bottom graph shows a deep, clear absorption signal, which is very sensitive to any extra heating from black holes. But the top graph shows a signal that is so weak, it's almost entirely washed out by the expected experimental noise. On top of that, there are also uncertainties in how black holes themselves work. The study compares a simple model for how black holes accrete gas, called BHL, with a more realistic one, PR, that includes radiative feedback. This feedback is like the black hole being a messy eater, pushing away some of its food with radiation, which drastically reduces how much energy it injects over time. This graph shows the final forecasted constraints on primordial black holes. The blue lines, using the simpler accretion model, suggest future 21 centimeters data could be incredibly powerful. But the red lines, using the more realistic model, show that the constraints would be much, much weaker. In the less constraining scenario, the data would provide no new constraints at all. So let's recap the important takeaways. First, our ability to find new physics with the 21 centimeters signal is critically tied to our understanding of the first stars. The difference between an optimistic and pessimistic model isn't a minor tweak. It changes the forecasted sensitivity by several orders of magnitude. Second, the theoretical models used to describe the new physics also have a huge effect on the outcome. To truly unlock the potential of 21 centimeters cosmology, scientists will need to use other instruments, like the James Webb Space Telescope, to learn more about the cosmic dawn. Only then can we confidently separate the signal of the first stars from the potential whispers of new physics. Thanks for watching Summarize Science.